All right, a few other ways to combine sets here, just combinations of these intersections, unions, complements ideas. Um, the empty set is interesting. If U is the universe that we're dealing with, the universe being the total number of elements, if U is the universe, then the complement of the empty set is the universe. Okay, the complement of the empty set. Everything that's in the universe but not in the empty set is everything. Right? Nothing's in the universe anyway. Or I'm sorry, nothing's in the empty set anyway. Also, if we had, let's say in this example here, if we intersected some complements, let's do something like E complement intersect T. It's kind of an interesting one. You find the you find the complement of E and then intersect that with T. Sometimes you can do that right off the Venn diagram. In fact, if I was to do that off the Venn diagram, E complement is everything not in E, so I kind of ignore the E portion, and I've got these other 5 elements, and then intersect that with T, so it also has to be the stuff in T, so you take out, so then you just look at the stuff in T that's not in E, and you end up with just 3 and 9. Oops. So equals 3 and 9. Now that's from the Venn diagram. I'll abbreviate it VD there. So that's from the Venn diagram. Now you could also do this by listing out the sets in roster notation and looking at their overlap. So if I listed out E complement, and I know E complement is going to be, it's going to include 1, 3, 5, 7, 9, right? It's all the odds. And I'm intersecting that with T. Now T I already know to be 0, 3, 6, 9. And if I look at all the elements that are in both, 1 is not, 3 is, 5 is not, 7 is not, 9 is. So it's just going to be the set 3, 9, and again I can get that from the roster notation or from the Venn diagram. Either way you want to look at it. Okay. And of course you can do some tricky things, right? It doesn't have to just be with this set, but we can look at complements. We can actually intersect 2 complements. We can do unions with complements, and really just start to combine some of these things and see how they all interact. So maybe we do E union with T complement. Let's try that one. I'm just making some stuff up, just scrambling things. Obviously, I can't give you an example of all the different combinations, but it would just take too long. But at least give you an idea and a feel for how to construct these. So E union T complement. Again, you could pull it right off the Venn diagram. You could look at everything in E, which is this circle of evens, and then anything that's not in T, which would be all the 1, 5, and 7, and then union them. Union means you just pull them all together and make one big set out of them. Okay, so from the Venn diagram, I would see that as 0, 2, 4, 6, 8, 1, 5, 7. So 0, 1, 2, 4, 5, 6, 7, 8. 4, 5, 6, 7, 8. Okay. If I was doing this off of the roster notation, I'd take set E, which I know to be 0, 2, 4, 6, 8. Union that with T complement. Now T is all multiples of 3. T complement then is anything not a multiple of 3, which is 1, 2, 4, 5, 7, 8. Right? Yeah. 1, 2, 3, 4, 5, 6. Yeah. Okay, it should be 10 total. That's right. 6 here, 4 there. So the sum of the cardinalities is kind of interesting. The cardinality of a set and the cardinality of its complement add up to the cardinality of the universe. They should. Okay, so I take these two and then I take the union of them, which just means I write all the elements without duplicating any. Okay, so I want 0, 1, 2, 3 does not show up, 4 I want, 5 shows up, 6 shows up, 7, 8 shows up in both, and 9 doesn't show up. So there we go, and it should be the same list as I had up here from the Venn diagram. Okay. So, yeah, that looks good. Now, in the next video, we're going to go through some of the cardinality combinations.